Oh, thank you.
So good afternoon to everyone. So I am Tagliabue, a PhD student from University of Verona. I've just realized that I'm the first female presenting. I don't know if the only one, I hope not. Anyways, I'll try to represent the women community in the simulation field. So today I'll talk a bit about the ways to model the interaction between the ultrasound probe and the soft tissues during robotic ultrasound scanning procedures. But before going into that, I would like to just say a few words about the activities that we're doing in my lab in Verona. So the main field of expertise of our lab is in robotic surgery, and in particular, our main goal is to develop methods to automate most of the tasks during robotic surgery. So we have the Da Vinci research kit in Verona, and most of our research is around this system. Then, always related to the surgical field, so we also work with simulation. There you can see a simulation in Unity where we were sort of simulating the partial nephrectomy. So we are displacing the fat on top of a kidney. And always in the field of simulation, there is a startup which started from our lab whose name is BBZ. So this startup develops both the hardware and software components for of this system. So here on the left, you can see the console they are using. So this console mimics the manipulators of the Da Vinci system, so the two handles. And so the main advantage of this console is that it can be easily brought around. Indeed, it can fit into a cabin luggage, and it can be really moved from one place to the other. So the console can be used both to drive tools in a simulation environment and also to drive real tools. For example, it was used, as you can see in the video there, to control the real and effectors of the Da Vinci system. So the console that is shown there is one previous prototype. So let's now pass to the topic of my presentation. So my talk will focus on the Mural project. So it's a project that we as University of Verona collaborate to as partners. And one of the tasks of this project is to perform a robotic-assisted ultrasound scanning. And the target anatomy is the breast. So the target application is breast biopsy. So as you could see from the video, one of the main challenges of the ultrasound scanning is that the breast deforms a lot due to the interaction with the ultrasound probe. And it's very important to model these deformations for two main reasons. First, in order to track the internal targets and how these targets, so the tumors, move when the probe presses against the breast. And second, in order to plan the optimal trajectory for the robot. So what we try to do in Verona is to compare different modeling strategies in order to account for the probe-induced deformations. So there are three main ways to model the interaction between the ultrasound probe and soft tissues. The first way can be to use penalty forces. So this is usually the default method when collision detection is involved, and it's the default method because it's very easy to implement and usually very fast. But the main drawback of this method is that so the penalty, when we apply penalty force, we basically define some spring-like forces between the interaction nodes. So the extent of these forces heavily relies on the contact stiffness, which is the proportionality coefficient between the amount of interpenetration and the applied force. And the simulations can become really unstable depending on the value of this coefficient, which depends in turn on the ratio between the stiffness of the contacting objects. Then there is another method which is based on constraint forces. So the main advantage of this method is that the interpenetration in this case is completely avoided. But on the other hand, we have to define some constraints. So the equation systems system becomes more complex and more computationally demanding to solve. A final alternative is to model this contact as with the Dirichlet boundary conditions, so by imposing surface displacements, and in this way, so imposing the displacement of the surface of the object such that it follows the displacement imposed by the probe. So the equation system in this case is much simpler, but the main drawback of this method is that it's necessary to define a priori which is the contact area. So we decided to evaluate the performances of these three different approaches, and we did it within the SOFA framework in order to have a common platform for everything. We used a patient-specific model of the breast, and we assessed three main performances criteria. So we did this experiment where we used a multimodal breast phantom and a freehand ultrasound system. We tracked the position and orientation of the ultrasound probe in space with an optical tracking system, and the experiment consisted in applying 4 different levels of probe-induced deformations to each of the 10 internal lesions of the phantom. In addition to comparing these three FEM-based modeling approaches, we compare them with a non-physically based method, which relies on the position-based dynamics approach. And I don't have time to go deeper into details for this approach, but if any of you is interested, I would be happy to explain something more. So here are the results we obtained. So from an accuracy point of view, all the methods get errors which are aligned. So what we can notice is that the error actually increases with increasing extent of input deformation. So I think that the most interesting results are those related to the computational time and the stability of the simulations. So from a computational time point of view, from this table, from this figure, it clearly emerged that the method based on constraints is the one taking most of the time, while all the other methods are close to the real-time threshold that we fixed to 25 frames per second. And the method relying on position-based dynamics approach outperforms all the others, but this is mainly due to the fact that the implementation we were using is the one provided by NVIDIA Flex, so it's highly optimized and on GPU, so we were expecting that. Anyways, it's the only method able to keep the simulated time and the computational time always equal for all the simulations. Another result which was of interest for us was from a stability point of view. This is very important, especially within a robotic framework, where the stability of simulation really plays a role into into the planning, for example. And so what we did here was to assess the percentage of simulation which was successfully completed by each method for all the tumors. And what emerged is that the only method, FEM-based method, which was able to be stable in all the cases, is the one where we were prescribing the surface displacements, while all the methods where we were explicitly modeling the contacts were at a certain point a bit unstable. As we expected, the most unstable one was the one based on penalty forces. So from this comparison work, it emerged that the different methods have achieved different trade-offs between accuracy, stability, and computation time, and also from a generalization capability point of view. And the choice of the method really depends on which are what is required by the simulation. Anyways, the method which seemed to perform better is the one which prescribes surface displacements, even if it has the constraint that the contact area must be a priori known. However, even though this may be a limitation in some applications, in our case, it's not a strong limitation, since by planning the robot motion, we can know in advance which is the area where the robot is going to hit the surface. And so I think that this comparison between these methodologies can be of help in a general sense for everyone who is trying to model the interaction between a rigid object and a deformable object. I would just like to spend a few words on this project that I developed in collaboration with the Mimesis team in Strasbourg, where we basically tried to do exactly the same that we were doing with a regular FEM, but using a neural network. So what we were doing here was to train a neural network with finite element simulations, and a lot of finite element simulations of several probe-induced deformations, and then we were using the network to predict the volumetric deformation of the breast for new unseen data. So what emerged from this work is that the accuracy achieved by the network was completely comparable to the one of the finite element model used to train the network, but the computational time, as you can see there, is reduced of more than 100 times. So it seems that exploiting machine learning methods is very promising, is a new trend, and from both an accuracy and a computational time point of view, it seems the way to go, and it can also be fed with real data, so it has the potential to be updated intraoperatively with the data acquired maybe either during the intervention or during the scanning itself. So, and this concludes my talk. So, for any of you looking for collaborations, so if you want to come to Verona and visit our lab, we also have many positions available. So we're open to internship opportunities, master theses, and we also have some postdoc positions. So, and if you have any questions, please feel free to ask. Thanks.
So yeah, you're definitely right. That's something which is for a long time true in the SOFA community. There is a strong lack of female researchers or engineers, definitely. Thankfully, there is Nora, you, Maud also in the room, so that's we are not losing hope for getting a 50-50 percentages in the SOFA community. Thank you very much for the presentation. Is there any question? Yeah, I was expecting some.
Yeah, my question is about modeling of the breast tissue. How many different material characteristics did you take into account? Did you model the skin in a different way than the inner tissue?
No, so actually we were modeling just the breast as a homogeneous object, but at least not using a linear elastic law, but a hyperelastic law, which made actually the modeling of the contact even more challenging. But no, we were not, at this stage, we were not taking into account any heterogeneities and not the presence of multiple materials.
I have another question on exactly the same topic. Actually, when I read the abstract, it was one of my questions. Actually, it was, and I didn't see. I don't think having here the answer. It's a Neokian model, if I'm right. And you said that there was patient-specific parameters, and how do you estimate those patient-specific parameters?
Yeah, so unfortunately I had no time to dig into detail of everything,
yeah.
But yes, so it was, these were results of our previous work where we were using the same breast phantom and performing these experiments of passing from a prone to supine configuration. So we were trying to estimate which was the elastic modulus of the breast based by simulating the change of position of the patient and validating the model against also standing position.
Empirically, or there was some optimization loop for that, or some filtering for that?
Yeah, there was an optimization loop for that. Yes.
Okay, cool. So yeah, I also noticed we were a bit late. So thank you again, Eleonora, for the presentation.